Good morning, everyone. So we start our third lecture about machine learning. So I'm sharing my screen, make a slideshow from the current slide. So I switch. Yes. Okay. So last time, last time we discussed, but basically, I just want to repeat these briefly, these ideas about how to get to a kernel and how the gram matrix, like the gram matrix product of vectors, supporting vectors, is virtually the key. I mean, it's a key feature, key point of the method. So we suppose that we have some geometry well, Euclidean geometry, and we can work out applying the standard geometric algebraic tools, right? First of all, so we have at least two groups of points, and we believe that there should be a plane, hyperplane in multidimensional space, or a line in the simplest case, which definitely and reliably separate these two groups of clouds, these two clouds, okay? Typically, if we work on the computer, we should give some precise scenario how to calculate this line, and then the answer might be that we should formulate some kind of optimization problem on these points. And indeed, there might be infinitely many such hyperplanes or lines which separate groups of points. And the idea is that we are searching for such a configuration, such a hyperplane or such a line, which provides the biggest distances, possible distances, margins between one cloud and another cloud. Well, you see, it's our choice. For particular problems, you might change the rules. Well, so how to find the equation for such a hyperplane? And I told you that basically I use this metaphor, this example as a metaphor at the very beginning, at the very first lecture, when we tried to construct a linear classifier separating dogs from not girls but cats. Sorry. And we just search for some. In my case, I told you that X and Y might be concentration of red and green and blue colors within a picture. You see, I'm repeating this just to give you an idea that it might not be X and Y or some numbers. It might be some physical parameters, like amount of color in a particular ink, or some percentage of infected individuals, and so on and so on, in order to, for instance, classify different treatment strategies. Okay, so, and then, okay, so the classification is that if some combination exceeds some threshold, then we have one group of individuals or points. If it lays below some threshold, then it's a green group of points. Okay, so that is so you see that this is what people call a linear classifier. We live in a linear space. Let's just work out this example first. Then we just discussed that, okay, so we are searching for such line with a margin. We call all these a decision surface, such that which you know touch the margin points. And then the question, so I'm trying to establish such a direction for my line to get maximum margins, so minimum distances from some margin point here to this line on the both sides. Intuitively, it's clear that okay, you know, mathematics is only a language to explain or to describe trivial engineering solutions, right? So here, it's clear that the parameters of my line should depend upon at least 2 or 3 points which are on the margin. So therefore, this method is called margin classifier, linear margin classifier. What we are going to construct now, it's just a linear margin classifier, and these points, critical points, which determine the position of my, I mean, the precise equation of my line is called support vectors. And the whole method is called support vector machine. Machine because it's not human who would perform all calculations, trivial calculations, but a computer. So in the support vector, because we are searching for some points which might be in conflict, right? So we should decide to which side, to which group we classify them. Well, again, so what should I say? That we have some input vectors, all lines, it's just linear equations. Some coefficient w, x, plus some constant. Okay, there might be, okay, so one, yeah, maybe here even the picture is clear. So here the equation is that for support vectors, I should have w times x, scalar product, minus some constant b is equals +1. So I suppose that they belong to a particular class +1. And then here, I will use pen. So here I have +1, and here for a negative group, I have -1. The line, the equation of line is just wx, scalar product of wx equals b. The distances, d plus and d minus, I would suppose them, I suppose the problem symmetric. And I would think for such cases where d plus and d minus in absolute value are the same. Simply for, you know, just to simplify calculations. The shortest distance to the closest positive point and the shortest distance to the closest negative point, respectively. So they are called the margins. We suppose that margin is the same on positive and negative sides. So we have, we try to maximize these margins. Okay. So now, next step. Well, clearly we should find a classifier with which provides us big margin, as big margin as possible. So, and we know that distance from point to a line, I guess it's calculus 3 or something. I mean, calculus 3 probably the part about planes and distances between points and lines. So you, if you have a line given by the equation, by a linear equation, then you can calculate this distance using the coefficients a and b and the c specified in the equation. Therefore, I can rewrite my problem here. I can rewrite my problem as the distance between, searching for distance between h and h1, here d plus, because I believe that d plus and d minus is the same, is a scalar product of wx plus b in absolute value divided by the norm of the vector w should be equal to 1 over, oh, that actually means it's a distance. It's 1 over absolute norm of the vector w. So since I believe that negative margin and positive margin should be equal, I should take double 2 divided by norm of the vector w. So that is the function I'm going to maximize. Okay, so I'm searching for such a line which maximizes these quantities. Now, well, this is a quadratic optimization problem. So not maximize, sorry, it's just minimize, because well, it's in denominator. Okay, so it's just I should have its minimum value. Sorry for. Okay, so I should maximize 1 over 2 over double norm of W, but this means that I should minimize W. Okay, I don't know how to solve it, and nobody knows. So people solve instead the following quadratic optimization problem. Imagine a paraboloid, and we are searching for a minimum. So this is our surface. And if you remember the calculus 3, this chapter number, I don't know, 12 or 13 in our textbook, there should be, well, there is actually the problem like that were formulated, and we are searching for some, also for some constraints. We also have some constraints. So constraints are precisely defined by our conditions. Conditions that we should, well, we have these distance margins, okay? Either positive or negative margin is taken into account, should be taken into account, no matter, because I believe that they should be the same. And we have standard Lagrangian multiplier approach to solving this problem. So first of all, you see that we just replace, substitute the maximization of a norm by maximization of a squared norm. Okay, and then you remember probably that in the points we are interested in, the gradients on our surface should coincide with the gradients on our constraints. In our case, constraint is a line, okay, just a line. So we should have equation like that. And in standard approach, we are searching for coefficients lambda, which satisfy when this equation is satisfied for the given constraints. Well, we should calculate the derivative of the Lagrange functional, and set it to 0. So we have a Lagrange functional, set it to 0, and solve the optimization problem. When we try to solve the optimization problem, so basically that's what people call support vector machine. What computer is doing, it's searching for optimization, it's solving Lagrangian optimization problem, quadratic Lagrangian optimization problem with linear constraints. We get finally the following Lagrangian operator. First, this is a function which we are going to optimize. This is a set of constraints with some Lagrangian multipliers alpha I. Rigorously speaking, I should add here, include into my sum all points in my data set with some alpha. So I have for 1 billion points, I have 1 billion Lagrangian multipliers. And then I also request that all Lagrangian multipliers should be positive, because I'm interested in only in positive margin. Okay, so I have it. I can solve it abstractly. You know, I can solve it. The solution is linear, some linear combination with some given alpha. Well, it tells, and if I just look at the form of solution, it's just, you see, it's some linear combination. So it's a linear equation. Linear equation defines me a line. So it's a line. It's a particular line with some coefficients. If I play further, I would see that actually most of this alpha should be 0. Why? Because they are related to some points in the bulk, far from the margin. And then I conclude naturally that only some points very close to my line should have some non-zero Lagrangian multipliers. Namely, when I extend my margins, these are the first points I encounter. There might be not that many, actually 2, 3, typically, right? So one on the one side and a couple of another, or just one on another side in two-dimensional case. In many-dimensional case, I should have more points. But you know, anyway, it's everything is under control. Okay, now, nevertheless, the problem, if it's formulated like that, it would be a simple problem from calculus course. But then there is a step which is never given, never discussed in the calculus course, but always done in the real life when we solve the Lagrangian, the optimization problem by Lagrangian method. Maybe just because professors never do research themselves. I don't know. Okay, so suppose that's my initial Lagrangian. It was my initial Lagrangian. I guess the form of the solution. I'm not going to solve it. I'm going to plug the expression, or rather the general form for the expression for my W, for my vector describing the plane, back into my Lagrangian functional. Instead of W, I have here this sum. And then I have expression like that. So what is the meaning beyond this operation? I make a step from direct problem to so-called dual problem. In the original problem, I suppose that the value of Lagrangian functional is fixed, and I need to find some Lagrangian multipliers. That is the problem from a textbook, from the Calculus 3 textbook. Okay, typically we search for some multipliers, Lagrangian multipliers. Now, by doing that, I simply exclude, I exclude W from here by plugging it back, by plugging it into the Lagrangian functional. And then I have another problem. So all values of Lagrangian multipliers are fixed now. And I'm searching and I try to maximize the value of L given alpha, for the given alpha. So that is the function, new function which I should multiply. And you see that due to this condition, most of alpha should be zero, because I require them be non-negative, so they cannot compensate each other. So I should kill them somehow. Those alphas, for Lagrangian multipliers, alphas for those points which are far from my boundary, from my margins. So I should kill them. I just set them to zero. And then I have just sum which runs over some marginal boundary points here, here maybe, okay, which defines the position, of the line. What is the most important component here of my lecture? This inner product. This is inner product of these basically 3 points. So I have 3 by 3 matrix. This is a Gram matrix of this scalar product of these 3 points. Expressing similarity between certain support vectors. So I take few support vectors and calculate this Gram matrix, which describes me what people call similarity. Okay, so because a scalar product express similarity. If scalar product is high, they are similar. If it's orthogonal to each other, dissimilar completely, I have zero. That is why people call it similarity. All machine learning strategy by this time is based on substitution. These xi, xj by some not negative kernel. People call it kernel. A suitable function, a suitable matrix, which should satisfy the properties of Gram matrix. Gram matrix, it should be, the eigenvalues should be, there should be no negative eigenvalues. There might be 0 eigenvalues, there might be positive eigenvalues, but not negative. So whenever you have something symmetric, positive function symmetric, like Gaussian, you imagine a Gaussian, it's not bell-shaped, but in 2 dimensions and 3 dimensions, so on. As soon as you have something like that, it would work here. If people ask you, what the hell are you doing? You would answer, this is my kernel function. I work in a feature space. So in a feature space, I work not in the real geometry of these axes, where these axes were first taken from, but in some curved geometric space in which the transformation might be nonlinear. Instead of these axes, you might, in simplest case, use the kernel for random walks. You see the first hitting time or commute time might be considered as a kernel here. Okay, so but this is a completely, I mean, in a naive machine learning approach, people either take vectors as they are, then that is called linear classifier, linear support vector machine, or quadratic functions, that's called quadratic support vector machine, or some nonlinear approximations, or some kernels which might follow from some, I don't know, evidences that this kernel works well for a particular problem. So people actually, or data scientists are paid for searching and finding a gram matrix or kernel which works well for the particular problem. So that's what I wanted to see. Again, so primal version of classifier is linear. Dual version of classifier is with a gram matrix here. Well, yes, so that's what I already told you, that many of these alpha are zeros. And finally, we have contributions, non-trivial contributions, only from points which are close to the boundary, from support vectors, which support the surface or hyperplane dividing the clouds. Yes. Okay. What people might do. Not always, it is not always possible to get clouds separated like that. Sometimes we need, we have some problems where we have polar symmetry or spherical concentric symmetries, logarithmic symmetries, anything else, and then coordinate transformations might be useful. So this is an intermediate step which I actually omitted when I explained you the situation a few minutes ago. So toward the kernel, there was, when people started to think about kernels, they first used different coordinates, like polar coordinates, to, reveal the geometry of the problem, which would reveal the geometry of the problem, and then you would get finally the situation like that. So coordinate transformations. After doing coordinate transformations with different coordinates, they realized that in principle, they might use any kernel, good enough kernel, which works like a gram matrix, which works as a scalar product matrix. Well, yes, so in principle, in the examples which I sent you, which we are going to consider now in MATLAB, in this MATLAB file, that's the standard situation which we will work out. Now I stop sharing. This is the last slide of my show. I stop sharing and I open my MATLAB file. I open my MATLAB file. And yes, it's opening. And I share my screen again. Yes. Here I close it. Discard. Sorry. Yes, I just in case I will. I hope you see. Yes, I hope you see the screen. Okay. So this is the file machine learning AM which I send you. first, classification by support vector machine. Let's upload the Fisher Iris data. I use the original, I mean, I've form it in the Fisher Iris comma separated format into a single table. You remember that if I would just type Fisher Iris or load Fisher Iris or something like that, there will be a MATLAB structure. But I need a single table, a comma separated format, which is most suitable for what I'm going to do then. Okay, so I just going to show this table. I added the last column species into a single as a last column within the table. Okay, now yes, now what I'm going to do, I'm just open applications, choose the classification learner. You see that there is a curve which separates on the icon, which separates the clouds. Okay, start a new session using a file which I already. Okay, and what you see, what's actually what I have here. I have my measurements, columns with measurements, and the final column with species, which is categorical. Therefore, it given gray. By default, it's what is used for. So it's the idea that classification, it's a categorical learning. So we should we should be able to develop, to find some patterns on some part of the data, which I declare as training data, and then check, found some, I mean, take some random 5 elements, 5 flowers, and by comparing with these patterns, I should identify them, to which patterns they belong to. Okay, so this is precisely what we did the last time with dendrograms, right? Basically, we found the closest elements. Now we do basically the same, but it's called now machine learning. Well, simply because we try to do it using this Lagrange optimization problem. Okay, I'm starting the session. And the very first algorithm which it might give me, which is used by default, it's a tree structure. That is what we used for the first time, say before we started the machine learning. The same example, dendrogram and calculation of distances based on this petal width, length, and others. Now, I'm just pressing the point. You see that I have several options, all linear classifiers. Find trees. You see there are a lot of kernel, naive bias, bias classifiers, Gaussian naive bias, and so on and so on. If I know which kind of classifiers I like to use, but I know that, for instance, more classifiers, more hypotheses I use, the better are my results. So I press the point all. Why there are so many options? And then I just don't forget to press train here. So it would open parallel port. Why there are so many options? Because my data might be not 150 flowers. It just, nothing. It might be hundreds of thousands or even millions of readings. Now it produces, it just gives me all options, and then I would observe. So here I have accuracy 94%. This is highest accuracy, 97%. All others, so it's done basically, right? Linear discriminant analysis and quadratic discriminant analysis. We will discuss precisely this method a little bit later, these methods of machine learning. Well, I just choose, for instance, a linear discriminant analysis. Okay, well, then so scatter plot. So it provides me some my classifications, which was in the last column. And well, they were in principle identified accepting incorrect points. Incorrect points here marked by crosses and apparently lay on, you know, on the boundary between these, we'll say, actually between the second and third classes, between versicolor and virginica. Well, what else I can show? I just plots. Okay, so I see the problem. Why? Yes, I used to have it on the. Now, this is what you see now. It's a scatter plot. It just gives you a visual impression of how the learning had been performed. Now, if you need a precise information about errors, so you might draw what is called a confusion matrix. So this is the matrix between true classes and predicted classes. On the major diagonal, you have number of true defined flowers. So there were 50 flowers in each group, and the 2 flowers were misclassified between versicolor and virginica. Two versicolor were classified as virginica, and 2 virginica were classified as a versicolor. So this is precisely the structure what happened. If you have many classes, you at least might see the problems of the approach. I might change to quadratic discriminant analysis. And then I get, you see, in the first case, it was the errors were balanced. Here we have kind of asymmetry. Versicolor 3 times was identified as virginica, and 1 time virginica was identified as a versicolor. Okay, so there might be some curves which we will discuss later. Okay, so minimum classification error plot, not optimized. Okay, so for this it simply doesn't work. Here is also okay. Parallel coordinates plot also doesn't. Yeah, okay. So these are. We will discuss these approaches when we basically we will discuss the data exploration preliminary steps. But here, in principle, this is so-called parallel coordinates plot. It identified, so it used different colors for every learned. Okay, somebody, yes. Okay, so I think that hope that just have some people unmuted. Yes, okay. You see that they have different colors, and here are the measurements on the horizontal axis: sepal length, width, and so on.
Hello, Dr. Dimitri.
Yes.
We can't see any of the plots you are showing. I'm sorry.
Oh, Jesus. So have you seen this MATLAB?
Yeah, we can see the MATLAB window, but we can't see the plots, or at least I can't.
Okay. Okay, so, well, just a second. I will.
Dr. Dimitri.
Yes, I will make new share. Okay, so new share. Read this. Do you see it now?
Yeah.
Okay. Well, basically, I will explain then. I use the all button here just to implement all possible classifiers existent in the database. It shows me the best results, best accuracy is achieved for linear discriminant and quadratic discriminant analysis. We will discuss this method in details later. Then, okay, so I chosen the best, for instance, linear discriminant analysis, and show that first we can just get a general impression from the learned points, from the learned classes using the scatter plot, where the incorrect predictions had been marked by crosses. Incorrect predictions usually lay on on the boundary in between groups, classes. Don't be afraid that these cross points lay within these clouds. You have 4 measurements, not 2. So you have your points live in a 4-dimensional space. And the search by support vector machine, search was done in a 4-dimensional space. But then, to represent it in as a 2-dimensional plot, these points were projected on a 2-dimensional screen, so to say, right? So sometimes, even if you think that there is no linear boundary between these points, there is a linear boundary, but in a 4-dimensional space, guys. Okay. Now, well, I can also use a confusion matrix, which would give me precisely the number of misclassifications between versicolor and virginica and vice versa. In this case, the misclassification is symmetric, but if I use, for instance, quadratic discriminant, I just press the quadratic discriminant option in my methods, and then I get, you see the asymmetric misclassifications. Versicolor was 3 times misclassified with virginica and just 1 time backward. I can use construct the same confusion matrix for any used methods here. For instance, if I use, okay, k nearest neighbors here, k nearest neighbors, it would give me 3 misclassification of versicolor and 3 misclassification of virginica. Something with yes, shit. Something with very bad score, ensemble. It it correctly classifies cetosa, but lost in classification of versicolor and virginica completely, because it believes that cetosa is the only class within this within the database. So if you get something, I mean, if somebody, I mean, media or somebody told you that using machine learning, you identified those given classes, and they do not specify what type of methods they used, please be aware that using machine learning, you can get any result you like or you dislike. Complete freedom, absolutely. So everything should be specified. What did they do? Which method they used? And what are the accuracy? What was the accuracy derived at this method? Because if the accuracy is 30%, you see that 33%, it means 1/3. 1/3 means that they assumed instead of 3 classes, they got a single class. So they just merged all data together into a single class. So this is a very convenient method, and moreover, this is really wise to give you as many particular methods to test as many particular methods as possible, because if you remember, we have a trade-off. Our misunderstanding of the problem, first of all, we don't care about the relations between the variables and whatever, but instead we use many methods. So whenever you work with data, please use as many methods as you can. And the MATLAB, therefore, we like MATLAB so much because it gives us a chance to test many different methods at once. Now, so you could play with this data and with different methods. Now, train support vector machine classifiers using a Gaussian kernel. In most of cases, naive data scientists would use a Gaussian kernel function because they believe that in many practical situations, we have deal, in fact, with Gaussian kernels. So I generate 100, I'm going to initiate the random number generator in a seed. Okay, so now I'm going to generate two groups. Well, I use the normal distributions and sorry, and simply generate ellipses, randomized ellipses. Now I generate second group of points with the same basically parameters, but yes, parameters are different, but okay, so simply I multiplied by 3, so I will show you how it looks like. Oh, sorry. Yes, do you see the picture? Figure 1. Screen sharing is paused or what? Yes, so do you see it now?
Yes.
Okay, perfect. Yes, so what I did, I simply generated two groups of points. I mean, normal distributed 100 points. One is 3 times, with amplitude 3 times, one group is 3 times bigger than another one. So I get these two groups of points, and I am going to separate them by using the support vector machine classificator. Okay, D23. Yes, so I assign, now I assign ones +1 to one group and -1 to another group. And then I try, imagine that I don't have this nice application as a learning classifier, and I will do it by, you know, simply by choosing some linear method and show you how it works. So maybe from pedagogical point of view, I would start from this approach, but you know, I should just want to show you first how it works in general. So the comment is called the fit classes with support vector machine, fit CSVM. Data3, the class kernel function. Well, we will discuss all specifications a little bit later. So this is classes what I classificator gives me simply scores. So first, then I should draw what I get from my scores. So I define the grids, and now I construct the figure. My figure. Right. So I try to, so I assign negatives, -1, to red points inside in my inner, so to say, circle, and positive points in the outside. Sizes of points are given accordingly their scores within my support vector machine procedure. These are Lagrangian multipliers. If they are 0, I didn't touch them. If they are non-zero, I give some, their radius increased by 2. I'm sorry for such a representation, but that's what I wanted to say, that these are my support vectors. These are points which define me the boundary. Okay, so, and you see that the situations looks nonlinear because I can always use polar coordinates. That's what I did. In reality, I worked in a linear space, in fact, yes, but transformed by polar transformation to polar coordinates. But nevertheless, that's what I found. I found these points which I use to get my boundaries between classes. Initially, it was simply a circle, but that is what predicted by the boundary predicted by support vector machine, because it should touch every support vector. Now, what should I show you? Yes. Now, now I'm going to show you these shit. Now I'm going to show you basically the Gaussian kernels. Gaussian kernels. I will just show it to you. Right, it gives me a little bit different support vectors. Different support vectors. Train is using custom kernel. Yes, I'm just hurry up because of the lack of time, but maybe I will just repeat it next time. Yes, so probably this, because, well, I would just stop at this point because then I would start, next time I would explain, you know, I am at the very beginning of this, basically of my file, because I want also to discuss regressions. Okay, so let us stop at this point, and I will continue next time with precisely with these machine learning examples. But well, that's what I wanted to say you today, that in principle, you see that there are a lot of options, many different methods. Any method might give you, say, basically any result you like, but with some accuracy. So please check everything always when you try to classify categorical things. There is a special, just the last seconds, what I wanted to say, that there is a special approach for classification of non-categorical variables, because here we had, you know, discrete species of flowers in this example. But in principle, we might have something which is classified accordingly to some variable. And these methods are called regression. The meaning is the same in principle, but we live in a multidimensional space. But we believe that there is a surface in this space which would separate clouds of one quality of one particular features from others. And we are searching for some surface. It might be still a plane. It might be some curved surface. It's called a regression because it's not a categorical, but, you know, it's a real score which defines. And then the question is, what should be the values of? And the regression is used often for prediction. What should be the value? What might be the values of parameters to give a highest or lowest, for instance, score in a particular measurement? What should be the quality of soil to get the best quality of wine, red or white? What is the, in the example which is just given in my file, there is just what should be the quality, I mean the particular features of car, of engine of car to get the most outcome or minimize the consumption of fuel, number of gallons per 100 miles, for instance. Okay, so two types of two mindsets. First, categorical support vector machine, and then the same, basically the same methods for real values, not categorical but continuous case, and it's called a regression. And we will discuss it at the beginning of the next lecture, and then I will continue with the second part of machine learning. Thank you so much. Please do your, okay, some chat. Yes, yeah, perfectly. So please do your projects. If you have something to ask or discuss, don't hesitate to call me. As soon as I'm free, I immediately contact you. Because sometimes people just press this Zoom, but I am on the other Zoom. I mean, if they are not on the, well, in office hours, I might, you know, be just busy, but I see that somebody tries to enter and immediately contact. And please prepare your presentations because, well, you can do it at any time, basically, any time convenient for you. If you already have something to, you know, to present to your peers, please let me know, and then we organize a kind of a special session online. Thank you so much. Okay, have a nice day, safe weekend. So I stop sharing. I stop.